In this video, we're going to take a step back away from differential equations and just look at what this I imaginary number does for us and the kinds of constructions we can make with it. What we're going to do is define a new term, and that's going to be a complex number. And a complex number is something that's going to have two components. It's going to have a real component, and it's going to have an imaginary component. The nice thing about how these work is that they can be separated completely. We're going to have an x value. Actually, we're going to frequently call these z values. Z is traditionally a letter reserved for complex values. And what we can do is write this as a plus b times the imaginary number I, where both a and b are both real. What does that look like? That can be z equals 2 plus 3 i's, or that can be z equals 2i, or z equals minus 7 pi plus 6i. Any combination of a real part, so 2, 0, negative 7 pi, plus a real number times the imaginary I, that's going to give us a complex number when we add them together. Now, how does that fit in with what we already know? So we already know the real numbers. How does that relate to the complex numbers? Well, the real numbers are a subset. Sometimes that's written in set notation as this big cup thing here, sideways cup, as a subset of the complex numbers. How do we figure? Well, the number x equals 2 is a complex number. If we want to think of it that way, it's 2 plus 0i. There's no difference between these two numbers except what we're imagining the possible range of other numbers is. So the real numbers can be written as complex numbers, just with no imaginary component to them or no imaginary coefficient. But then a number like 2 plus 3i cannot be written as a real number. The inclusion of the square root of -1 opens up doors that are closed to purely real numbers. Once you get past the idea of I being the square root of -1 or I squared being equal to -1, then one of the beautiful things about complex numbers is how simple they actually are to deal with. Imagine taking just these two complex numbers. I know they're complex because there's a real part and a real times I portion to each one of them. And just imagining adding these like you'd add any other components of things. I have a 3 minus 1, so I'll have a 3 minus 1, just regrouping. And then I have 2 i's and I have 5 i's. Well, both of these have i's, it's a common factor, so I think I just get 2 plus 7i. And that's exactly right. There is nothing fancy you have to do here when computing sums of complex numbers written this way. Same idea with a negative sign. Just imagine that negative sign distributing over what's inside. So we have 1 plus 2i minus 2 minus I if we apply that negative to both terms. And then we just take the real parts because they're on equal footing, if you like. We take 1 minus 2 minus 1, 2i minus an I. That's going to give us 1i left over. And we just group those terms. If there's no i's, we do exactly the same thing we would have done in the good old days of real numbers. That's 3 plus 7 on the real part. And if I wanted to, I could have said, well, there's no I, so plus 0i in both cases. And I could have included that 10 plus 0i if I wanted, or we could just call that 10 like normal people would. The idea being, though, that what you know about real number addition is also covered by the rules of complex number addition. So real numbers are a subset of the complex numbers, and addition works exactly the same way it used to. We're not having to break any old rules to make up these new rules. Last but not least, what if we have an expression like this? Just remember that 0 idea can go the other direction. This 6i by itself is a complex number with 0 real part and 6 i's for the imaginary part. So we can still add the real parts and get -2, and 6i minus 4i is positive 2 i's, and so we can compute that sum as well. Now, I hope this is feeling like you've done this before. This is okay, I take the 3 and the -1, I add them. And then separately, I take the 2 and the 7, I add them. Gosh, that sounds familiar, because it sounds exactly like what we did with vectors. If we'd said, hey, if you can add the vector 3, 2 to the vector -1, 5, what would you do? Well, you would add the components separately. You get 2, 7, right? Well, that turns out to be another inspiration for how we visualize complex numbers. Remember when you first learned about real numbers and the number line, you'd say, oh, I could add things by jumping to the right and bouncing back to the left for subtraction, all that stuff. Well, the same basic premise is true for the complex numbers as well, only now we need to work out in a plane. So what we have is a horizontal axis that defines the real numbers, and then we have a perpendicular axis that is the imaginary axis. And that maps perfectly onto our inspiration from the last page about vector components. If we put the real components first, that's our x coordinate, our horizontal component, and that would have been our 3 plus 2 or minus 2 real part. And then the y component was our second term, and we added it separately, treated it separately. That's just our imaginary axis in this complex plane world. So there are tons of parallels to vector notation. There is some new stuff that gets tied into that, but for now it's enough to think of it as points on the complex plane. Just as a quick illustration, let's do some of those calculations and see how they play out in graphical form. So if we have one z value, that's 2, so real is 2, and 3 i's up here. Draw that line. That is z1. And z2 is 1 plus 2i. Let's do that separately. Sorry, 1 minus 2i, so that's down here. A little too rambunctious with the auto-locking, that's okay. That's z2. And just remember, if we did this z1 plus z2 with the symbols here, we would get 2 plus 1 and 3 minus 2i's. That would be plus I. And we can achieve that same goal just by doing the head to tail thing. I'm going to take this z2 and I'm going to move it up here like a vector. And there we go, z2. That head to tail does the addition. And what we get as a result is z1 plus z2. And just reading off the coefficients here, it's 3 and 1i. So, oops, not a vector. 3 plus the 1i value. Oh look, same as we got with the algebra. So adding complex numbers, if we imagine complex numbers being represented as a real line and an imaginary line perpendicular to each other, we get the same process as when we added vectors with x and y components. And just to quickly reinforce that here, let's take z3 plus z4 and we'll do it algebraically. -1 and 4 for the real parts, so that'll be 3. And there was an I, and there's no i's here, so we just leave it alone. We get 3 plus I. Drawing those out on the plane here, let's draw z3 first, -1 plus I, so that guy there. z3, and z4 is just along the axis. Let's do it in a different color than so it stands out. There's our z4. And if we do head to tail, we just move this, jump up to here, move it over, have it go for 4 steps. And sure enough, this point, I won't draw it as a vector, but this point is 3 plus I. 3 over 1 by I. So wonderful parallels with vector constructions. Is it all that easy? Not quite. We're going to see that when we get to multiplication, life gets a little more